Okay. So, today I shall discuss the Atiyah-Singer index theorem in the context of determining the chiral anomaly, that is the difference between the numbers of plus 1 eigenvalues, that is plus 1 eigenvalues fermions and the number of minus 1 eigenvalues fermions, where these plus 1 and minus 1s are the chiral eigenvalues, that is they are eigenvalues of the operator gamma 5. So, let us just see what it actually means. That we have to first define what are called characteristic classes. So, I will give you an example to illustrate it. This is called the Euler class. Suppose A mu is a one form on a Lie algebra. A mu is a Lie algebra valued one form, that means this can be written as A mu A of x into Ta, where Ta are the generators of the Lie algebra. And suppose I compute, so I can write down, I can consider the form A to be equal to A mu dx mu on the manifold. So, this is something like a gauge potential. If you take d of A, you get the field tensor in the abelian case, that is in the case when the Lie algebra when the Lie group is U1. So, you will get A mu comma nu dx nu wedge dx mu, which corresponds to the cross product of A. But in the non-abelian case, what happens is that when the Lie algebra is a non-abelian Lie algebra, say like the Lie algebra of UN or SUN or something like that, in that case you define a covariant derivative as d plus A, where d is the differential operator. So, what this essentially means is that in the language of, in a coordinate language, it means that del mu is equal to dou mu plus A mu, or this is same as dou mu plus A mu A into Ta. So, if you look at the curvature, so del is called the connection, the covariant derivative, gauge covariant derivative. So, suppose you compute the del with itself, the commutator of this with itself, that is called the field tensor, and that is nothing but d plus A comma d plus A. D comma d is 0, because when you apply it twice, d square is 0. So, this will give you dA, d acting on A plus A comma A in the language of forms, because d comma A is d acting on A, and A comma A, if it is a abelian Lie algebra, then A comma A becomes 0 and you get simply dA, which is namely the cross product of A, right. dA is nothing but the cross product of A or the curl of A. So, in the non-abelian case, this is what the field tensor looks like, and you can also write this as Fs dA plus A wedge A, where A, this is the skew symmetric product of the two forms A and A, of A with itself. So, you say that if you write A as A mu dx mu, then you can also write this as A mu in coordinate form Ta dx mu, then A with A becomes what? A with A becomes A mu A nu dx mu wedge dx mu. This wedge product takes care of the fact that you can put them in either order. You can write it as A mu, it is a anti-symmetrized version of A mu with A nu. So, this can also be written as A wedge A, can also be written as A mu comma A nu with a factor of half dx mu wedge dx nu, because this is anyway skew symmetric, that is you write A mu dx mu wedge dx mu, this is equal to minus A nu, this is equal to minus of A nu dx nu wedge dx mu, which is equal to minus of A mu dx mu dx nu. So, if you add these two and divide by 2, you can say that A with A is also A mu comma A nu, the commutator into dx mu wedge dx nu, into dx mu wedge dx nu after incorporating a factor of half, which is also equal to a mu a nu b, Ta comma Tb into dx mu wedge dx nu. But Ta comma Tb is given by the structure constants of the Lie algebra. So, you can write this as, you can write Ta comma Tb as f a b c t c summed over c, where c, f a b c are the structure constants corresponding to this basis. So, this can also be written as f c a b, you can write this as c a b into a mu a nu b dx mu wedge dx nu, which is nothing but FCAB a wedge AB. So, in other words, you can write the field tensor as, you could write DFS, you write Fs dA plus a wedge A, which is same as dA. In coordinate form, this is the same as if you write Fs Fa Fc Tc in the where Tc's are the generators of the Lie algebra, then you can see that Fc Tc is equal to dAc Tc plus FCAB dA wedge dB, dA wedge dAb into Tc, because when you take the commutator it becomes this sort. So, if you look at the Cth component of the field tensor, that is equal to dAc plus FCAB dA wedge dB, dA wedge dB, dAb. So, this is the field tensor in component form. FCAB are the Lie algebra structure constants. So, now you can define. So, you can define the, so this is the curvature or the field in general relativity. What happens is that you used a spinor connection, which means that the Lie algebra is generated by gamma mu comma gamma nu by 4. This is what the Lie algebra is generated by, and the spin connection can be written as, gamma mu, can be written as gamma mu, which is gamma mu AB, gamma A comma gamma B by 4, where gamma mu is derived from the spinor connection, the spinor connection of the gravitational field that can be derived that can be expressed in terms of the tetrad basis. So, your covariant derivative then becomes dou mu plus gamma mu. This becomes the covariant derivative, and what is the Lie algebra? Lie algebra is generated by gamma A comma gamma B by 4, which is nothing but the spinor representation of the Lorentz group. So, you can write this as AB into gamma AB by 4, where gamma AB means the commutator of gamma A with gamma B. So, gamma AB satisfies the Lorentz commutation relations, that means the commutation relations between gamma AB and gamma CD, they are the same as what you would get between the standard Lorentz generator in R4 or in Rn also. So, here the Lie algebra generators are specified by gamma AB by 4. The pair AB corresponds to the pair AB corresponds to the gauge index here. So, essentially when you apply this to the, when you formulate the Dirac equation by replacing the ordinary partial derivative dou mu by this gauge covariant derivative, then the Dirac's equation becomes invariant under under local Lorentz transformations and also under diffeomorphisms. So, provided you assume you postulate the correct transformation formula for gamma mu, the gauge transformation formula. Essentially, if you have dou mu plus gamma mu, you require gamma mu of x, you require that gx inverse, where g is the let us write it in this way. So, if d is the spinor representation of the Lorentz group, that means d of lambda is equal to exponential you can write this as omega mu nu gamma mu nu by 4, where omega mu nu are some functions and omega mu nu satisfy are antisymmetric, omega mu nu is an antisymmetric matrix, it is an antisymmetric matrix, that is omega mu nu is minus omega nu mu, and then you can write lambda, where lambda will be given by exponential omega. So, you can see that d of lambda becomes exponential d lambda acting on omega, which is nothing but exponential omega mu nu gamma mu nu by 4, or omega may be, instead of mu nu you can put a b here. So, the gauge, the covariant derivative transforms as what, d lambda x into dou mu plus gamma mu x into d lambda x inverse is equal to dou mu this will be nothing but this is dou mu under local Lorentz transformations, this is dou mu plus gamma mu dash of x, where gamma mu is the transformed spin-or connection. So, from this you can easily read out that gamma mu dash is equal to d lambda gamma mu d lambda inverse plus d lambda into dou mu d lambda inverse. It is the standard Yang-Mills transformation formula of the gauge potential, but now the Lie algebra is generated by, the Lie algebra is the spin-or representation of the Lorentz group SO31. That means it is the Lie algebra is nothing but dd acting on SO31, where d is a spin-or representation, and Dirac's equation remains invariant under Lorentz transformations due to this fact. So, and of course, you also, for example, if you start with Dirac's equations gamma mu dou mu plus gamma mu minus m psi equal to 0, if you put this is equal to 0, and where gamma mu is gamma a e mu a, where e mu a is a tetrad, then you can see easily that if you multiply this by d lambda x, that will also be satisfied, where lambda is a local Lorentz transformation, which amounts to saying that d lambda x multiplied by gamma a e mu a at x into dou mu plus gamma mu x minus m into d lambda x inverse into d lambda x psi x equal to 0. That means d lambda x psi x is a new wave function which satisfies this wave equation, and by using the commutation relations between the gamma matrices, you can show easily that d lambda x gamma a d lambda x inverse is equal to lambda b a x, sorry, it is equal to lambda a b x gamma b. So, from this it will follow that if you make a Lorentz transform, if you look at this equation, this is nothing but the Lorentz transform version, that is d lambda x psi x obeys the local Lorentz transform Dirac wave equation. So, you could also write this as lambda a b x gamma b multiplied by e mu a x into dou mu plus then this multiplied by this plus into dou mu plus gamma mu dash of x minus m acting on so gamma mu e mu a x acting on, if you call this as psi dash x, the transformed wave function psi dash x equal to 0. So, this multiplied by dou mu, okay. So, d lambda, you put a d lambda inverse here and you put a d lambda here, right. So, you write it as, essentially you write the equation as gamma a E mu A into dou mu plus gamma mu x, and you are putting a d lambda here and you are putting a d lambda inverse here, and you are writing it as psi dash equal to 0, but this is a local Lorentz transformation which can also be written as d lambda gamma A d lambda inverse into d lambda into E mu A d lambda dou mu plus gamma mu d lambda inverse this minus m is also there here that I missed out. So, minus m acting on psi dash. So, d lambda acts on, let us just write down the whole thing again, E mu A gamma A multiplied by dou mu plus gamma mu minus m acting on psi is 0. So, you put a d lambda here, you put a d lambda inverse here, you put a psi dash, which is psi dash is d lambda acting on psi. So, this becomes E mu A d lambda gamma A d lambda inverse multiplied by d lambda into d lambda will cancel out in the case of this mass, when you take into account this mass, this into this plus d lambda, this into this, and then d lambda into dou mu plus gamma mu d lambda inverse minus m E mu A into this whole thing minus m dou mu minus m psi. Okay. So, minus m acting on psi is 0, which is same as saying that E mu A into lambda A B into gamma B multiplied by d lambda. Okay, d lambda dou mu plus gamma mu dou lambda inverse gives you simply dou mu plus gamma mu dash, this minus m acting on psi is 0, psi dash equal to 0, psi dash. So, you are essentially transforming the index A in the tetrad, which amounts to performing a local Lorentz transformation on dou mu as well as on gamma mu dash, on gamma mu. That is, you this is nothing but the Lorentz transform version of the original equation. I can write this, I can assume that I can define E mu A dash to be equal to E mu B dash to be equal to E mu A multiplied by lambda A B, and then you get the same as you get the same Dirac equation as original, except that E mu A has been replaced by its local Lorentz transform version E mu A dash, and gamma mu, the spinor connection, has been replaced by gamma mu dash. So, now if you look at okay, now let us look at certain aspects. You want to the Atiyah-Singer index theorem tells you that if you look at the number of positive chiral fermions and the number of negative chiral fermions, the difference between these two numbers is nothing but the index of the Dirac operator, which is nothing but it is given by an integral of the form determinant r by sin h r power half into e power minus f, trace of e power minus f, where where this is the characteristic, this is the Chern character, this is called the Chern character, and this is nothing but this is the curvature tensor. R is a curvature tensor which is a two form, R is a is a matrix valued two form, it's a two form valued matrix, it's a matrix whose entries are two forms, that is the curvature tensor, whereas F is a Yang-Mills tensor, it is given by it is the curvature of the Yang-Mills potential. So, essentially you can say that F is nothing but F mu nu dx nu, which is nothing but d of d plus a with d plus a, which is nothing but dA plus a wedge a, where A is a Yang-Mills gauge potential Lie algebra valued, and R is a curvature tensor of the manifold. So, you have a differential manifold, you can look at it this way, you have a differential manifold and you have a tangent space at each point of this manifold, and apart from that you have it is a vector bundle, that is you have a vector space attached to each point where the Yang-Mills fields take values, Yang-Mills fields and potentials take values. So, you can look at the manifold in this way, M is like this, here you have the tangent manifold, this defines the curvature of the manifold R, the metric on this surface defines the curvature of this manifold. Apart from that you have a vector space attached which gives you F, right, at this point. You have a vector space attached at this point which is the Lie algebra of the gauge group, and you have this is the Atiyah-Singer index theorem, which tells you the difference between the number of fermions whose number of fermions means the number of 0 modes of the Dirac operator, which correspond to eigenvalue gamma 1 for plus 1 for the chiral operator gamma 5, and minus 1 n minus denotes the number of 0 mode eigenvalues of the Dirac operator, which correspond to the eigenvalues minus 1 for gamma 5. So, we will be proving this theorem soon, but let us just look at some consequences of this. So, especially in 4 dimensions what happens is that R is a 2 form, okay, R is a 2 form and sin h r. So, if you look at R by sin h r, R by sin h r, it will start with you expand it as in a power series. So, it will start with R by sin h r is an even, x by sin h x is an even function sin h x. So, it will start with 1 and then x square, x power 4 and so on in its power series expansion. So, if you look at x square, it will contain R wedge R with R wedge R, it will give a contribution R wedge R, but R wedge R is of course a 4 form, but it will not contribute because R okay. So, you will get a in 4 space you will have an R wedge R term coming from this, and R by sin h r is this. So, and if you look at trace of e power minus f, it will start that it will contribute up to, if you expand e power minus f, you get 1 minus f plus f wedge f and so on. So, since it is a 4 dimensional manifold, only this will contribute to the integral, this will not contribute to the integral. So, of course, in the space in the case of flat space time, it is only f wedge f which will contribute. So, the chiral anomaly comes out to be n plus minus n minus, which is nothing but integral of trace of f wedge f integral, which is a 4 form into a constant. So, the Atiyah-Singer index theorem reduces to this equation. Now, this is a topological invariant because n plus and n minus are integers. This is the index of the Dirac operator, which is essentially the number of you can also look at the index of the Dirac operator. If D is the Dirac operator, you can write it as 0 d plus star 0. So, if you look at d square comes out to be 0 d plus star 0 into 0 d plus star 0, which is nothing but d plus star 0 0 d plus star d plus. So, if you look at the super trace, if you look at the super trace of e power t d square, the square of the Dirac operator, super trace of this, there will be nothing but trace of e power t d plus star d plus minus trace of e power t d plus star, right. This partitioning of the Dirac equation of the Dirac operator occurs because the gamma matrix can be factored out into this form. The gamma matrix is this can be written as 0 sigma a 0, where sigma a's are the Pauli matrices, and sigma 0 is same as sigma 0, which is identity 2 cross 2 identity matrix. Sigma 1 is minus sigma 1, sigma 2 is minus sigma 2, sigma 3 is minus sigma 3. So, because of this you can factorize out the Dirac operator in this form even in curved spacetime. In curved spacetime, of course, gamma A is to be replaced by gamma mu x, which is gamma of E mu, or equivalently it can also be written as gamma A E mu A x, but this is the tetrad basis. So, if you look at the super trace of e power t d square, it is the difference between these two. Now, if you look at the eigenvalues of d plus star and d plus, if you look at the eigenvalues of d plus star and d plus star d plus and d plus star, all the non-zero eigenvalues are equal, including of multiplicities, which follows from the singular value decomposition. That means that if you look at the difference between the traces of these two, e power minus t d plus star d plus minus trace of e power minus t d plus star, then all this trace will be the non-zero eigenvalues of d plus star and d plus star d plus and d plus star are the same, including multiplicity. So, that will not contribute to the trace of this, the zero eigenvalues will contribute. So, essentially this will become equal to simply the nullity of d plus star d plus, that is the dimension of the zero eigenvalue subspace of d plus star d plus, right, minus the nullity of d plus star. You see what is e power minus t d plus star d plus, what is the trace of this? The trace of this is nothing but sigma e power minus t lambda over all lambdas varying over eigenvalues of d plus star d plus multiplied by taking multiplicities into account. So, if you fix the eigenvalue, if you sum over only the distinct eigenvalues, then you have to put a dimension of that space, dimension of that eigenspace for this. Similarly, for d plus star and whenever lambda is not 0, you will get the same terms, because the multiplicity is the same and the eigenvalue is also the same, so that will cancel out. So, only the zero eigenvalues will contribute to this super trace, but nullity of d plus star d plus is same as nullity of d plus. So, this can also be written as nullity of d plus minus nullity of d plus star, which is the index of the Dirac operator. It is called the index of d plus, or you normally just say that is the index of the Dirac operator. So, you see that you can write down the chiral anomaly as nothing but the index of d plus, and the Atiyah-Singer theorem tells you that this is a constant times trace of f wedge f in the absence of curvature. So, the Atiyah-Singer index theorem can be used to predict the chiral anomaly. What is the difference between the number of left handed fermions and right handed fermions for the Dirac operator. Now, this is called also given a special name, it is called the second Chern class. This is called the second Chern class of the manifold. That means trace of f wedge f is called the second Chern class, whereas f itself is the first Chern class. F itself is the first Chern class. Now, it is that brings us to the discussion of what is a characteristic class. Suppose I look at the following object, determinant of I plus constant times A, where A is a 2 form. A is a 2 form valued matrix, that means A is of the form, or let us call this as F, okay, let us call this as F, where F is equal to F mu nu x dx mu wedge dx nu, and multiplication is the wedge product while expanding this. So, if I look at the coefficient of t power n, okay, if I look at the coefficient of t power n, that will give you the nth Chern class. No, it will not give you the nth Chern class, it will give you the nth, I think it will give you the nth Pontryagin class, okay, and that will be invariant under rotations. That is because if you look at determinant of this, if you change t to if you change f to so f is a Lie algebra valued form, that means it is f mu nu, you can write it as f mu nu a Ta, Ta is a matrix. So, if you change this to G f G inverse, where G is any matrix, then this is the same as determinant of I plus Tf, because this whole thing can be written as G times I plus Tf G inverse, and the determinant of this is the same as determinant of I plus Tf. So, in particular, if you look at the coefficient of t, it is trace of f, which is the first Chern class, which is 0 in this case, because Ts are antisymmetric matrix, or Ts have trace 0 in the case when the Lie algebra is SUN. Okay, when the Lie algebra is SUN, then F has trace 0. So the first chain class won't compute, if you won't contribute. If you look at the T square term, if you look at the coefficient of T square, it will be F wedge F into some constant. It is because it will be a trace of F wedge F, it will be a trace of F wedge F. That is because if you write down the coefficients of, you can look at it this way also. If you take any matrix F having eigenvalues lambda I, then determinant of I plus Tf is nothing but the product over all the i's of 1 plus T lambda I, and the coefficient of T square here is lambda I lambda j, summation I less than j. This is the coefficient of T square in this expansion, where lambda i's are the eigenvalues of F, and this can also be written as summation lambda I whole square minus summation lambda I square divided by 2, but sigma lambda I is the trace of F which is 0. So this gives you minus half sigma lambda I square, but lambda I square is nothing but the trace of F square, right. So you can write this as minus half trace of F square, but what is F square? By F square I mean F wedge F, multiplication in the skew symmetric, in the space of skew symmetric forms. So trace of F wedge F apart from a constant gives you the second Chern class, and this is a topological invariant. This is a topological invariant. It is also an invariant under gauge transformations. It is also an invariant under gauge transformation, because if you replay under a gauge transformation, what is a gauge transformation? A gauge transformation takes d plus a. I am saying, I am writing f as the curvature of the connection, which is a wedge a. So under a gauge transformation, d plus a comma d plus a is f, which is dA plus wedge a. Under a gauge transformation, what happens is that a goes to what is the gauge transformation? Gx d plus a Gx inverse is equal to d plus a dash, which is same as saying that a dash is equal to Ga G inverse plus dg multiplied by G inverse. This is the gauge transformation. Under this gauge transformation, if you look at the commutator, what will it go to? It will go to G times d plus a comma d plus a G inverse. This commutator will go, because when you multiply G d plus a G inverse again G d plus a G inverse, it will give you the G and G inverse will cancel out. So this is nothing but GF G inverse, right. So and you know that determinant of I plus Tf is invariant under this transformation, GF G inverse. So or you can also look at it this way. If you look at F wedge F, what does it go to? It goes to GF G inverse wedge GF G inverse, which is nothing but G F wedge F G inverse. No, you can look at it this way. See, GF G inverse wedge GF G inverse. G inverse is nothing but G wedge G, G wedge G, F wedge F, G wedge G inverse. Right, by G wedge G I mean that it is same as G tensor G, but it acts on the skew symmetric tensor product space, and the trace of this will cancel out. G wedge G is the inverse of G wedge G inverse, G wedge G inverse is the inverse of G wedge G. So the trace of this will become, if you compute the trace, you will get back trace of F wedge F. So the second chain class is also invariant under gauge transformations, and it is a topological invariant, that is that follows from the fact that if you distort the connection slightly, then F will change, but since the integral of trace F wedge F is a number, is an integer, is an integer n plus minus n minus, this cannot change, this can change only by discrete jumps. So if you distort F A by the gauge potential by an infinitesimal quantity, this cannot change. That means it is a topological invariant, and it is also a closed form. That means d of trace F wedge F is 0. This is 0. It is a closed form. How do you prove that it is a closed form? Simply look at F wedge F, write F as A dA plus A wedge A, write it in this form. So that df, so that if you look at d of this quantity, of course these are all non-commutative matrices. F is a form, F is a matrix valued form, it is a matrix valued form. So you cannot, so you have to write it as df wedge f plus f wedge df, because it is a 2 form, d will slip inside. You see, if you take 2 forms, let us say this is of degree p and this form is a skew symmetric form of degree q, then you know that d of omega wedge theta is nothing but d omega wedge theta plus minus 1 power q omega wedge d, minus 1 power p omega wedge d theta. Here it is a 2 form, so this will slide here. So if you look at d of f wedge f, that is nothing but df wedge f plus f wedge df, which is equal to, use the fact that df is d of a plus a wedge a. So this is nothing but dA, and d square a is 0, so this is nothing but d of a wedge a, a is a 1 form, so this is nothing but dA wedge a minus a wedge dA. So this can be written as dA wedge a, wedge f minus a wedge dA wedge f plus another similar term like this, which df coming to this side. Now if you look at dA wedge a, what is it equal to? It is dAA wedge AB into TA TB, that is what is dA wedge A. What is A wedge dA? That is same as AB wedge DAA into TBTA, but you can, since dA is a 2 form, you can bring this to this side without changing the sign. So this is the same as DAA wedge AB multiplied by TBTA. So this whole thing, the difference of these two is nothing but DAA wedge AB into TA comma TB wedge f. Right. So this is the same as, and then you are going to take the trace of this, right. When you take the trace of this, what happens? It becomes equal to DAA wedge AB wedge SC multiplied by trace of TA comma TB into TC. F is a 2 form, right. So essentially, and you will get a similar term for in the second case, right. When you look at f wedge df. So essentially what happens is that your d of f wedge f, trace of this is nothing but FC wedge DAA wedge AB. You can slide in FC to this side, right. FC's are all scalar valued forms, because FC is the component of the F is equal to FCTC, TC's are matrices. So here you will get TA comma TB multiplied by TC, and then you get a trace here. Now this can be written as FC, you substitute for FC. So FC is what? FC is, you can substitute and show that all cancellations will take place. Instead, it may be more instructive to do it this way. If you look at d of f wedge f, this is df wedge f plus f wedge df. If you look at the first term, it is nothing but dA wedge A, wedge f minus A wedge dA wedge f, which is nothing but dA wedge A wedge dA plus A wedge A minus A wedge dA times, then the wedge product you take here, wedge dA plus A wedge A. So you are going to take the trace of this finally. So if you look at the term involving 2 ds like this one, dA wedge A wedge dA, and here you have another term minus A wedge dA, wedge dA, wedge dA. Okay. If you look at this term and you look at and you take the trace of this, what do you get here? You get daa wedge AB wedge DAC into trace of TA TB TC, trace of this. Here you get minus A. I will put the index B for A here. So I will slide, these are two forms, so I can bring this to this side. So this will be daa, it will be dA wedge AB wedge DAC. Okay. So trace, okay, daa DAB DAC. So okay, so you can write this as your A, you put an AB here, put an AB here, you put an AB here, you put a daa here, you put a daa here, and you put a DAC here. So here you will get TB, TA, TC, TB, TAC, TC and trace of that. These two are the same, right? If I can slide AB to the middle here because this is a 2 form. So this form is the same as this form, right? So this essentially you get daa wedge AB wedge DAC multiplied by TA TB TC minus TB TA TC, trace of that. So trace of TA comma TB multiplied by TC, that's what you get here. And then obviously here, and this is symmetric with respect to interchange of A and C, that because dA is a 2 form, daa is a 2 form, DAC is another 2 form. So if I interchange A and C, nothing is going to change here. So I can as well permute, I can interchange A and C in this expression and add them and divide by 2. The coefficient, it will give you the same coefficient of this. So essentially you can see that this is the same, this coefficient is the same as TA comma TB multiplied by TC plus trace of TC comma TB multiplied by TA. And what is this? This is TA TB into TC, trace of TA TB into TC minus trace of TB TA into TC. Here you get TC TB into TA, right. So you get TC TB into TA minus TB TC into, so if first term will be what? TA TB TC here. Here you will get TC minus TC TB into TA. And of course you can sum over all the, you can interchange A and C here, right? You can interchange A and C, so you get this, and this should be 0, right? TA TB TC, TA TB TC minus TB TC TA, TC TB T, it is minus TB, sorry, this is a term, okay, this will contribute a term TA TB TC, trace of this, and this will contribute a term minus of trace of TB TC TA, but TB TC TA trace is same as trace of TA TB TC. So this will cancel out, right? This will give you, this gives you TA TB TC, TA TB TC minus TB TC TA. You can bring TA to this side because trace AB is trace B, and that will cancel out. Likewise the second term will also cancel out. So this will cancel out, right. So the coefficient involving, the coefficient of the term involving product of 2 differentials daa and dac along with AB, that will contribute 0. Likewise if you look at the coefficient of the term involving 3 A's and 1 dA, what do you get here? You get dA wedge A wedge A wedge A 3 times, here you get, and here you get dA. Okay, now when you can slide in these two, this because A wedge A is a 2 form, you can bring it to this side, so it will become minus A, it will become what? It will become minus of A wedge, I can bring the dA to this side because dA is a 2 form, so it will be minus dA, I bring dA to this side, wedge A wedge A wedge A, and that cancels out. The term involving 3 forms also cancels out. three A's, that will also cancel out. So you get the result that f is a trace of f at f is a closed form. Trace f at f is closed, is a closed 4 form, but it is not exact, not necessarily exact. So you are integrating a closed form over the manifold. You are integrating the closed form over the manifold and getting the index of the Dirac operator from the Atiyah-Singer index theorem. I shall come to the proof of the Atiyah-Singer index theorem much later on, but this is a very important fact. More generally, you can define the Euler class, or you can define a whole sequence, whole set of characteristic classes by taking, for example, if D is a symmetric tensor, D I1, I2, etc. In. Suppose a manifold is a 2n dimensional manifold, okay, dimension of M is 2n, and suppose you consider Fi1 wedge Fi2 extra wedge Fin, okay, then this is a closed, summed over the repeated indices I1, I2, In, then this is a closed form, right. You can show that this is a closed form. So how do you show it is a closed form? Provided D is an invariant tensor, it is invariant with respect to the Lie algebra of the group. So if you look at D of this, what is it? This is di1, I2, etc. In. If you look at Fi1 wedge Fi2, they are all 2 forms, etc. At the kth position you take df ik, and then you put again wedge Fin and summed over all the k's, okay, summed over all the I1 to In's and also summed over all k going from 1 to n. So you write df ik. What is dfi? What is df of a? df of a is nothing but, remember what was f? F was dA plus a wedge a. So df was nothing but dA wedge a minus a wedge dA, minus a wedge dA. So if you substitute for this into df ik, if you substitute for this into df, you can also write this in component form as df of a is nothing but dab wedge ac dA wedge into tb comma tc, and you are going to pick out the coefficient of this into Ta is given by this, which is same as saying that dfa is nothing but dab wedge ac into f of bca, because tb comma tc is f of bca ta. So essentially if you try to compute d of d I1 to In Fi1 is a wedge Fin, if you compute the d of this, then this is nothing but d of I1 to In Fi1, etc. At that point you put a GAB here, GAB wedge Fin, at the kth position you put a GAB and multiplied by IKAB, where GAB is nothing but DAA wedge DAB. So now what does this mean? This means that if you are assuming D to be a symmetric tensor which is invariant under the Lie algebra. So if you assume that summation d I1 to In multiplied by f IKAB and summed over all the IKs, suppose this is 0, that means the structure constants are invariant under the action of the Lie algebra, then D of this becomes 0 immediately. For example, in the case of 2, what happens is that you have Fi, you have if you look at just n equal to 2, if you take n equal to 2, so that is a 4-dimensional manifold, and suppose you consider f of dAb fa wedge fb, and I take the d of this, what do I get? I get dAb into dfa wedge b plus dAb into FB wedge DFA, sorry, FA wedge DFB, FA wedge DFB, and then I substitute DAB. I write it as let me do it this way, let us write it as DIJ FI wedge FJ, FI wedge JJ. If you take the D of this, then you get DIJ, first you will get a GAB wedge FJ into FIAB plus DIJ into FI wedge GAB into F of JAB. So, I can interchange I and J here without changing anything. So, this will become J because this is a symmetric tensor, and here also I change I here. So, essentially this becomes the same as this, GAB tensor Fj is same as Fj tensor GAB because they are both two forms. So, essentially since Dij is an invariant tensor, you have FIAB is 0 summed over I, this is 0. So, this will also become 0. Likewise, in the general case it also follows that. So, you see that this quantity is a closed form I1 to In Fi1 wedge Fin, this is a closed form whenever Di1 to In is a symmetric G invariant tensor, symmetric invariant G invariant tensor. So, this is a closed form. If you specialize this to the curvature form, if you specialize this to the curvature form where Fi1 is replaced by FAB or you write it as okay, is replaced by FAB, where AB are the spinor indices. So, you are replacing Fi by FAB, that means this is equal to, here what is meant by saying Fi, it means Fi mu nu dx mu wedge dx mu. Here FAB means that FAB mu nu dx mu wedge dx nu, and what is, and when you put the index I here, what does it mean? It means you are multiplying it by a Lie algebra element Ti, the Lie algebra element Ti to construct the form. Here also you will multiply by TAB, but here TAB is the Lorentz, it is gamma AB by 4, where gamma AB is gamma A comma gamma B, it is a spinor index when you look at the curvature tensor. So, in that case what happens to this? If you choose Di1 to In in a particular way, if you choose if you look at, okay, let us call it as FAB, okay, FAB is a two form, FAB mu nu dx mu dx mu. If you look at the form sigma I1 or sigma A1 sigma A2 into F, of course when you say multiplied means I am taking the wedge product of this, F sigma A3 sigma A4 extra wedge F sigma An minus 1 sigma An, and you sum over all the sigmas, then you get the Euler class that amounts to, where sigma is a permutation of sigma A1 sigma A2 sigma A2n minus 1 into 2n, it will come out to be like this, where sigma contained in all permutations S2n. So, here you are choosing as it essentially amounts to when you take any thing of this sort, it amounts to multiplying it by epsilon A1 A2 etc. A2n, where you are constructing a symmetric tensor, right, Di1 I2 In on these indices. That symmetric tensor amounts to simply a permutation. That means when I look at Di1 to In, here there are two indices, I1 corresponds to A1 A2, I2 corresponds to A3 A4, I2n corresponds to A2n minus 1 A2n. So, you are looking at a symmetric permutation, you are looking at a permutation of all these things, all these indices. So, that gives you a symmetric tensor, right. So, it is a special case. In that case, this is called the Euler class, and the integral, the Atiyah-Singer index theorem tells you that the integral of this over the manifold equals the index of the operator, of the Dirac operator in 2n dimensions, or it is also called the Euler characteristic, it is also called the Euler characteristic. So, if you look at, for example, the Atiyah-Singer index theorem, determinant R by sin h r power half wedge trace of e power minus f. In the case when r is absent, okay, or when r is absent, then you get simply and you are integrating it over a 2n dimensional manifold. Then if you expand e power minus f, the only term which will contribute is f wedge f etc. to n times, so that you get a 2n form, and then you integrate that over the volume of the manifold and take the trace of this and integrate over the manifold and multiply it by an appropriate constant. That will give you the index of the Dirac operator, which will give you the chiral anomaly in multiple dimensions. So that much is about this. Now let us just look at a supersymmetric proof of the Atiyah-Singer index theorem to make things more clear. Let us look at a supersymmetric proof of the Atiyah-Singer index theorem. So supersymmetric proof is the following: the trace, you are computing the super trace of e power minus t d square. Super trace of this we have seen for any t, this is the index of the Dirac operator. This can be written as index of d plus, and this is nothing but trace of e power minus t d plus star d plus minus trace of e power minus t d plus star. So this is nothing but super trace of e power minus t d square. So to compute this index we need, this is also called the heat equation approach to the index theorem, because e power minus t d square is a heat kernel. It's e power minus t d square acting on any function psi will satisfy del psi by del t equal to minus d square psi. So it satisfies the heat equation. So let us just compute in the case of the Dirac equation this. So you have here the Dirac operator which is d, or this is same as gamma mu x del mu, where your del mu is dou mu plus a mu. A mu is just connection, it can involve both the contributions of the Yang-Mills connection as well as contributions of the tangent bundle connection, namely the spin connection, it can involve everything. And gamma mu x is nothing but gamma a e mu ax, it can also be written as gamma a multiplied by e mu, or gamma of e mu. So it is a linear functional of e mu of the tetrad basis. So you look at the fact that gamma a comma gamma b, this anti-commutator is 2 eta a b, Minkowski metric. So that will imply that gamma mu x comma gamma nu x, this anti-commutator is 2 g mu nu x, because of the fact that the metric tensor g mu nu can be written as e mu ax e nu bx into eta ab. So now you compute the square of the Dirac operator, gamma mu x del mu square, you compute this square, this is nothing but d square, this is nothing but gamma mu del mu, then gamma nu del nu, which is same as gamma mu, first take the covariant derivative of gamma nu multiplied by del nu plus gamma nu del mu. Now if you look at gamma mu del nu, what do you get? Gamma mu of this, what is this? This is del mu of gamma of Ea of E mu, which is nothing but gamma times del mu of nu, del mu of E nu. Now if the connection, this can also be written in terms of the connection, you are looking at E nu is a basis for the tangent space, E nu is a basis for the tangent space, not for the it is a basis for the tangent for the bundle space. So E mu a are the tetrad vectors. So if you look at del mu acting on E nu, in that base you can write it as gamma alpha, so if you write it as del mu acting on E nu, this is gamma alpha mu nu into E alpha, or equivalently del mu acting on E nu is gamma nu mu alpha E alpha, where gamma nu mu alpha are the connection coefficients. That is, you can express the covariant derivative of a vector field is again a vector field. So it can be represented as a linear combination of these basis elements E alpha. So you get that if you look at the square of the Dirac operator, d square becomes gamma mu gamma nu gamma mu del nu plus gamma mu into del mu gamma nu multiplied by del nu. Now, this portion can be written as, we have just seen that this portion is the same as gamma of E nu and del mu, which is gamma of gamma nu mu alpha E alpha, which is nothing but gamma alpha gamma nu mu alpha. So, the second term can be written as gamma mu gamma alpha into gamma nu mu alpha del nu. And the first term, what about the first term? The first term is of course symmetric with respect to interchanges of mu and alpha. So, this could also be written as g mu alpha times this quantity. So, essentially since gamma nu, this is the Christoffel symbols, these are the Christoffel symbols, this is symmetric in mu and alpha. So, I could replace gamma mu gamma alpha by gamma mu gamma alpha plus gamma alpha gamma mu by 2, which is twice g mu alpha. That means I can replace this by g mu alpha. Look at the first term. What is the first term? The first term can be written as gamma mu gamma nu del nu, which is gamma mu comma gamma nu half plus half gamma mu comma gamma nu multiplied by del mu. This is a commutator, this is an anti-commutator. So, this is the same as g mu nu times del mu plus half, here you have gamma mu comma gamma nu. Now, I can replace this by the antisymmetric part of del mu because this is an antisymmetric term. If you multiply, if you take the dot product between an antisymmetric tensor and a symmetric tensor, you get 0. So, it is enough to consider the antisymmetric portion of this, the symmetric portion will not contribute to this, and divide by 2. So, you get this. So, this is nothing but g mu nu del nu plus 1 by 4 gamma mu comma gamma nu. Then here I can write it as r mu nu, where r mu nu is the curvature of the manifold. Del mu, it is a 2 form, del mu comma del nu is not the Ricci tensor, it is the curvature tensor. When I say that is the curvature tensor, what I mean really is that r mu nu can be written as r mu nu a b e a okay, it is it's nothing but r mu nu can be written as r mu nu a b into gamma a b by 4, right, and gamma mu nu a b by 4, where r mu nu a b is a total curvature. It consists of both the curvature coming from the tangent bundle, spin connection of the tangent bundle, or equivalently coming from the gravitational field, as well as that coming from the Yang-Mills field. So, this whole thing becomes this whole thing B square contains a term like g mu nu of x del nu plus r mu nu of x into gamma mu nu into gamma mu nu by 4. So, r mu nu will partition out into 2 portions. Now, you apply what is called the, so what is del mu? Del mu is nothing but the spin covariant derivative. The spin and Yang-Mills both are involved, gamma mu x, where gamma mu contains the total connection of the spin as well as the Yang-Mills field. So, now you apply the Getzler scaling argument. What is Getzler scaling? If you take any form omega, any omega form and you operate on this by S epsilon, then S epsilon omega will be nothing but minus 1, or it will be epsilon to the power, epsilon is a positive real number, minus the degree of the form multiplied by omega. And of course, S epsilon acting on a bosonic variable, bosonic function of the bosonic field function is f of epsilon x. So, if you look at, for example, gamma A, if you look at gamma A, what is gamma A? This Dirac matrix. This can be written in the language of forms as EA plus EA, where EA is a one form and EA is a contraction form. That means EA is a contraction and EA is a one form. That means EA creates, whereas EA annihilates. You can write down the gamma in this form. That is because that if you take the dot product between EA and EB, if you take the anti-commutator between EA and EB, then you will get delta AB. You get delta AB. EA is a creation operator, EA is an annihilation operator. So, automatically if you use the, and of course EA, if you use the anti-commutator between two creation operators EA and EB, that is 0. Likewise, the anti-commutator between two annihilation operators EA and EB, that is also 0. So, this will imply that gamma A comma gamma B, will be 2 delta AB, or it will be 2 delta AB. It will be 2 delta AB, which is the required anti-commutation relation. So, if you now so on this manifold, so now suppose I take any form, let us say I look at the form gamma A, I write gamma A as EA plus EA, okay. I write it in this form and I consider S epsilon acting on gamma A. I am trying to take the trace, okay. Let us look at it this way. I want to compute omega is any form, I want to compute S epsilon inverse, I want to compute this. Let us say omega is a function of x also. So, I want to compute S epsilon omega x, S epsilon inverse. What does omega epsilon do? It may omega may either create or annihilate or some mixture of forms it is, right. So, suppose I consider S epsilon omega x acting on S epsilon inverse and then acting on some other form, let us say theta x. Suppose I look at this, then this is nothing but S epsilon omega x, then if theta has a definite degree, then this is epsilon power minus dou theta, okay, minus dou theta multiplied by theta x, and then this can be written as epsilon power minus dou theta, I can bring it outside. So, S epsilon multiplied by acting on omega x with theta x, the product of these two. But now this has got degree omega, this has got degree omega plus degree theta. So, this is epsilon power minus dou theta into epsilon power epsilon inverse I am putting. So, it should be a plus dou theta, the degree of theta should be like this, and this is nothing but plus dou theta, then epsilon power minus dou omega product with theta. Actually, it is not a wedge product, it could also be a contraction, right, or it could be a mixture of that. You are multiplying the two forms. So, the form may be either the operator may be either a contraction or that is an annihilation or a creation or a mixture of creation and annihilation. So, if you take S epsilon acting on this is minus dou theta, epsilon minus dou theta, because the degree of omega plus omega theta, the degree of omega wedge theta is nothing but the degree of omega plus the degree of theta power minus theta multiplied by omega wedge theta. So, this omega epsilon power plus dou theta cancels out with epsilon power minus dou theta, you get back this thing. So, essentially and you have to take into account the fact that you are scaling it, you are scaling the bosonic variable x also in the Getzler scaling. So, here you will get first when you apply this you will get a epsilon x, epsilon inverse x. Just let us see, let us do it again. S epsilon omega x, S epsilon inverse acting on theta x is equal to S epsilon omega x epsilon power dou theta into theta of epsilon inverse x. Epsilon theta inverse x, which is equal to epsilon power dou theta into s epsilon acting on omega times theta epsilon inverse x acting on this, which is epsilon power dou theta multiplied by epsilon power minus dou omega minus dou theta into omega of epsilon x into theta of x. The second Getzler scaling by s epsilon will take the x here to epsilon x, and epsilon inverse x, it will go to epsilon into epsilon inverse x, which is epsilon x, which is x. So, you get this, and this will cancel out with this. So, this is nothing but epsilon power minus dou omega multiplied by omega epsilon x. So, in conclusion, what you can say is that the Getzler scaling, if you acting on a function of x which takes values in the space of forms, is nothing but epsilon power minus dou omega multiplied by omega of epsilon x. So, I can take the super trace by applying the Getzler scaling and take the limit as epsilon goes to 0. So, if you look at d square, what is it? D square is nothing but g mu nu of x del nu as the first term, and then you have another term. Apart from that, you have r mu nu of x. So, let us call it as it is the sum of all that, right. So, it is r mu nu x, or it is, let us call it as f mu nu. Okay. So, it is f mu nu of let us call it as k mu, I think k is a better number, k mu nu of epsilon, k mu nu of x into gamma mu nu into gamma mu nu, right. Now, this can also be written as g mu nu x into dou mu plus gamma mu x a b. This is gamma nu a b x into gamma a b. That is what is the spin connection, the connection taking into account, of course it takes into account the Yang-Mills connection as well as the spin connection. So, this multiplied by dou nu plus gamma nu a b x gamma a b plus k mu nu of x into gamma mu nu. Where k mu nu consists of both the curvatures, the spin curvature as well as the Yang-Mills curvature. I can also write it as k a b gamma a b, will cancel out. So, I can also write this as k a b of x multiplied by gamma a b, where gamma a b is gamma a comma gamma b, and I have transformed into the tetrad system. Now, if you make a Getzler scaling on this, what will happen? G mu nu x will go to g mu nu of epsilon x, of course the bosonic part. Dou mu, I am scaling bosonic variables by x goes to epsilon x. So, dou mu will go to what? If x goes to epsilon x in the bosonic scaling, dou mu will go to epsilon inverse dou mu. So, it will become simply epsilon inverse dou mu plus gamma mu a b of epsilon x. What about gamma a b? Gamma a b can be written as gamma a comma gamma b, right. Now, what happens to gamma a? What happens to gamma a? Gamma a can be written as Ea plus Ea. So, gamma a under Getzler scaling will go to what? E superscript a is a creation operator. So, it will go to epsilon power minus 1 Ea, whereas E subscript a is an annihilation operator, that will go to epsilon times Ea, right. So, what is happening is that your Laplacian g mu nu epsilon x into epsilon inverse dou mu plus gamma mu nu plus gamma mu a b x into gamma a b you have here. So, that gamma a b will become what? You have a gamma a b, your gamma a b is nothing but gamma a comma gamma b, and gamma a goes to epsilon inverse Ea plus epsilon Ea under Getzler scaling, and if the limit as epsilon goes to 0, this will become 0, you will get only a creation operator epsilon inverse. So, in that limit what happens is that this becomes epsilon power minus 2 Ea wet Gb, Ea wet Gb. That is a Getzler scaling argument. It is like converting a quantum mechanical problem into a classical problem, because in quantum mechanics you used a gamma matrices. In classical field theory you use exterior forms and integration of forms over manifolds. So, this will go to this, and then you have another term like that. So, of course, there is an epsilon x sitting here, because the bosonic variable also gets scaled epsilon x. Similarly, you have epsilon inverse dou nu plus gamma nu a b epsilon x epsilon power minus 2 Ea wet Gb. Now, now you choose a coordinate system such that the connection vanishes, the derivatives of the metric vanish at those points, at that point. You choose a local coordinate system in which gamma mu a b vanishes at x equal to 0. So, in the limit as epsilon goes to 0, if you assume, you can always assume that the connection is such that gamma mu a b 0 is 0, because you are, it is a condition only at one given point. So, you can always choose a coordinate system so that this happens. And if you expand, if you write gamma mu a b of epsilon x as gamma mu a b at 0 plus gamma mu a b comma nu at 0 into epsilon nu into epsilon x nu by Taylor expansion, epsilon x nu by Taylor expansion, and you others are order epsilon square terms which are much smaller, then this term epsilon inverse dou nu plus this whole thing, that will become epsilon inverse dou nu plus what is the derivative, what are the derivatives of the connection at 0, that is nothing but the curvature tensor, right. So, it can also be written as, and one epsilon here will, and one here you have an epsilon power minus 2, here you have an epsilon. So, the product will give you an epsilon inverse term, only an epsilon inverse term will survive, and here you will have r mu nu r mu nu a b at 0 into x nu into Ea wet Gb, where r mu nu a b is the Riemann tensor, Riemann curvature tensor. So, essentially this whole covariant derivative becomes, the idea in Getzler scaling is to reduce the computation of the trace to the computation of simply the trace of a matrix, instead of having to compute the trace of an operator which is defined on a differential manifold. So, it localizes the whole problem and converts it to simply a matrix problem by eliminating the dependence on x, So, here what you get is that your G mu nu after Getzler scaling this into epsilon x multiplied by epsilon inverse into dou mu plus r epsilon inverse into r mu nu a b at 0 multiplied by x nu multiplied by Ea wet Gb multiplied by another term epsilon inverse dou nu plus similarly epsilon inverse r nu alpha, say let us put it as nu alpha instead of using the variable nu, I put mu alpha x power alpha. So, nu alpha a b at 0 into x alpha into Ea wet Gb plus other terms. So, the epsilon inverse comes out, it becomes epsilon in power minus 2 times G mu nu at 0, because epsilon is going to 0, and here you have dou mu plus you write r mu nu a b Ea wet Gb. You see what is happening is that you are having gamma a b, right. When you have gamma a b, it is gamma a comma gamma b. If you look at gamma a gamma b, this is Ea plus Ea into Eb plus Eb. After on Getzler scaling, this becomes epsilon inverse Ea plus epsilon Ea. This becomes epsilon inverse Eb plus epsilon Eb. The product of these two gives you epsilon power minus 2 Ea into Ea. Only the creation will survive, because that gets scaled by epsilon minus 2, whereas the annihilations get scaled by either annihilation, product of two annihilations gets scaled by epsilon square, and the product of a creation with an annihilation gets scaled by epsilon, which will all vanish in the limit. So, you can write this as I call R mu nu A B E A where G B as simply a matrix at the point 0. I call this as simply as R mu nu at 0. So, this is R mu nu at 0 multiplied by x nu and then I am getting a square of this. Square means I take an identical, or let us put alpha in place of nu, alpha here, alpha here. That means I write, what is the meaning of square? Square means I write the same thing with mu replaced by nu and then you sum over all the g mu nus. So, what this means essentially is that this is this into dou nu plus R nu alpha 0 into x alpha, right. So, this becomes simply, and you have also a curvature term, that curvature term was R, it was k mu nu at 0 at epsilon x, k mu nu at epsilon x into gamma mu nu, or k a b it was, right. So, it was k a b into gamma a b, which also got scaled by epsilon power minus 2 into gamma a b into E a where G b, E a where G b. Essentially you had k a b of x into gamma a b. So, on Getzler scaling this becomes k a b of epsilon x into epsilon power minus 2 E a where G b, because gamma a b on Getzler scaling becomes epsilon power minus 2 E a where G b. The other terms are either of order epsilon minus 1 or of epsilon 0 or of order 0. So, only this will survive in the limit. So, finally what happens is that this becomes an ordinary, this becomes simply a linear differential operator, it becomes the square of an operator of this form. So, your square of the Dirac operator becomes what after the Getzler scaling? That means you multiply by S epsilon here d square S epsilon inverse, then this becomes simply epsilon power minus 2 g mu nu 0 is simply that. So, it is dou mu, I can write this in this way, I can write it as dou plus r, dou plus r0 x, dou plus r0 x square, dou plus r0 x square, where r0 is a 2 form, r0 is a 2 formed valued matrix plus something like epsilon power minus 2 k a b at 0 into gamma a gamma b. So, it was this into k at 0, where k is again a 2 form. Actually k will consist of 2 terms, it will consist of the curvature coming from the spin connection of the gravitational field as well as that coming from the connection of the Yang-Mills field. The connection, the term coming from the gravitational field will be what? It will be of the form R mu nu a b gamma a b, and then again you have a gamma mu nu, right. So, in local coordinates I can write it as gamma c d a b gamma c d, and by manipulating this is a product of 4 gamma matrices. By manipulating I can show that this becomes simply the scalar curvature into the identity matrix by using properties of the Riemann tensor, namely it is skew symmetric with respect to interchanges of the last 2 indices as well as skew symmetric with respect to interchanges of the first 2 indices, and it is symmetric with respect to the interchange of the pair C D and A B. If you use that, this becomes simply the scalar curvature or Riemann scalar curvature Rx into an identity. So, that will not contribute to the form, only you will be left with the Yang-Mills contribution which I call as F. So, essentially I am writing Kx as the one coming from the gravitational field plus the one coming from the Yang-Mills field, and I am left with only the F term here, F0. So, now the question is how to evaluate e power minus t d square super trace of this. So, super trace means you are first you must compute e power minus t d square. When you compute, this is nothing but the harmonic oscillator Hamiltonian, because it has got a square term in the position, it has got a square term in the momentum, and it has got a bilinear term in the position and momentum. All the other things are constant and this. So, the question amounts to how to compute e power minus t d square, which amounts to computing the evolution, a complexified version of the evolution operator of the harmonic oscillator Hamiltonian in n dimensions, So, and we know the result, that the result is if you this result can be written as e power minus t d square, and so I am going to take the super trace of this and then take limit t going to 0. I can take limit t going to 0. So that will give you, so essentially I have to compute exponential minus t by epsilon square into dou plus r0 x square plus r0 x square plus f0, where f0 is a 2 form, r0 is also a 2 form. So you have to compute the evolution operator of a supersymmetric harmonic oscillator. Supersymmetric harmonic oscillator, because the Hamiltonian here becomes a 2 form. These potentials r0 is a 2 form and f0 is also a 2 form. It is of the form, you can say r0 is nothing but rab at 0, eab at gb. Likewise f0 is fab 0, eab at gb. So this quantity comes out to, now I can let t go to 0, epsilon go to 0. So this is irrelevant as far as the trace is, super trace is concerned. The value of t and epsilon square were irrelevant as far as super trace was concerned, because of the fact that the trace of super trace of e power t d square gets contribution only from the 0 eigenvalues of gets contribution only from the 0 eigenvalues of d plus, right, d plus and d star plus. Essentially e power minus t d square super trace, I showed that this was nothing but the nullity of d plus minus the nullity of d plus star, and it does not get contribution from the either eigenvalues of d plus star d plus, the non-zero eigenvalues of d plus star d plus are the same as the non-zero eigenvalues of d plus star because of the singular value decomposition. So it gets contribution only from the 0 modes of the Dirac operator, right, it gets contributions only from the 0 modes of the Dirac operator, and computing this super trace, so computing this exponential is nothing but computing the evolution operator of a supersymmetric harmonic harmonic oscillator Hamiltonian, and we know that the result is sin h r for the normal Hamiltonian, determinant r power half into e to the power minus f0 into e power minus f0, which is e power minus f0, and here when you multiply the two matrices, it amounts to multiplying them as forms. This is a matrix valued form, this is another matrix valued form. So you multiply them as forms and matrices, and when you take the super trace, since the gravitational curvature has disappeared here this is a normal EA, is a normal exterior form. So this becomes, the super trace becomes simply trace of this quantity, which is the trace of the Chern form, which is a Chern character, and e power minus f0 is nothing but the curvature of the manifold, or the curvature of the vector bundle, or equally the curvature of the Yang-Mills field. So this is how you come to Atiyah-Singer index theorem, by using the formula, it is called Mehler's formula for the evolution operator of a Hamiltonian in n dimensions. So you will get simply the result that n plus minus n minus is the index of the Dirac operator, which is nothing but a constant times integral of determinant of r by sin h r power half multiplied by trace of e power minus f. And in the special case when there is no curvature, it becomes simply the Chern character, and this is also called the Todd class, this r by sin h r, and it will start with the second order. You see, if you expand determinant of r by sin h r power half, it will start with degree 2, it will start with degree 1 and degree 0 and degree 2, because this is an even function of r. So the first non-trivial term, it will be a 1 plus r wedge r, it will start with 2. So whereas trace of e power minus f will have f1 minus f plus f wedge f by 2 factorial plus etc plus minus 1 power n f wedge extra wedge f power n by factorial n, and so on. And you take the trace of all this, you get, if it is an 2n dimensional manifold, only the nth fold anti skew symmetric tensor product of f with itself will contribute to this integral, and that is the whole story. Next time we shall see, next time we shall talk something about, we shall discuss something about things like complex structure on a manifold, and how the complex structure, how do you deform the complex structure, and how is the deformations of the complex structure related to the 0 modes of the Dirac operator. So, essentially we will show that the deformations of the complex structure are essentially the set of cohomology classes of type H21 on a complex scalar manifold, and H21 is the cohomology class. That means it consists of all 0 modes of the Dirac operator, which are forms of type 2 comma 1, that is 2 in the holomorphic index, 2 in the holomorphic indices and 1 in the anti holomorphic indices. So, from that we are able to, we will be able to compute dimension of H21 using algebraic geometry, namely using the fact that by taking a quintic polynomial and considering manifolds of SU3 holonomy, we will be able to compute the dimensions of H21, and because the dimensions of dimension of H21 is essentially the dimension of the space of deformations of the complex structure, essential number of degrees of freedom involved in the deformation of the complex structure, and that will be and H21 on the other hand is nothing but the number of zeros of the Dirac operator, in the cohomology class 2 comma 1. So, we will be able to relate the two, and that will enable us to compute not just the chiral anomaly, but also precise values of n plus and n minus. So, it is the fact that you can compute H21 by simply looking at deformations of the complex structure or equivalent in terms of quintic polynomials. It is one of the wonders of algebraic geometry that you can go beyond the Atiyah-Singer index theorem, which involves only computing the chiral anomaly. You can compute the exact values of n plus and n minus in various cases by simply looking at by simply counting the number of degrees of freedom involved in the deformation of the complex structure. Let us stop at this point. Thank you.